Welcome back to Understanding Signal Isolators, Converters, and Interfaces. Previously, we broke down the differences between 4-wire and 2-wire isolators and how their power architectures affect output capability, load handling, and installation requirements. We also covered where each type fits best and why insufficient power levels can have a direct impact on accuracy and long-term stability. Without foundation in place, this video will shift focus and walk through the basics of signal conversion and how signal converters also perform critical roles in process control and monitoring. Signal conversion plays a vital role in process control by ensuring that different instruments and receiving devices are compatible when different signal types are utilized. Converters make it possible to translate legacy signals like 10 to 50 milliamps or 0 to 5 volts into today's standard 4 to 20 milliamps that your control system can read. We'll look at several types of converters: fixed range units built for simplicity, field configurable and PC programmable models that add flexibility and precision, converters designed to step down high-level AC signals safely, and modern digital solutions that map HART data to Modbus for seamless integration into plant networks. Signal conversion is the process of translating one type of process signal into another, allowing instruments, transmitters, and control systems to communicate accurately across generations of technology shifts. In many plants, older or legacy devices still output signals like 10 to 50 milliamps or 0 to 10 volts, which may not align with modern systems standardized on 4 to 20 milliamp current loops. A signal converter bridges that gap by accepting one signal type, isolating it from interference, and converting it into another format that your receiving device can read and respond to reliably. Converters don't just change signal formats. They also scale, linearize, and protect process signals from electrical noise and ground issues, ensuring consistent and dependable measurements. In short, signal converters make sure that no matter what kind of signal your equipment sends, your control system receives a clean, usable, and accurate signal. Now, let's take a closer look at the main types of converters and how they differ. When it comes to signal conversion, there are three main approaches: fixed range, field configurable, and PC configurable signal converters. A fixed range signal converter is designed for one specific task, like converting 0 to 10 volts into 4 to 20 milliamps out. It's simple to install, just mount, wire, and go. But that simplicity comes at the cost of flexibility. If your application changes, a fixed range converter can't easily adapt to new signal types. A field configurable signal converter, on the other hand, allows you to rearrange inputs or outputs using switches or jumpers. It takes a little more setup, but this flexibility means one device can handle multiple applications, reducing the number of spares you need on hand. Finally, PC configurable signal converters offer even greater flexibility, precision, accuracy, and control. They allow fine-tuned range settings and software-based adjustments without physical switches or jumpers. In addition, they can easily handle reverse output, split range, and custom linearization scenarios. Next, we'll look at how signal converters can safely step down dangerous AC signals for monitoring and control. When most people think of isolators, they think of DC signals, solving problems at the instrument or control system level. But signal converters also play a critical role in monitoring, trending, or alarming on AC signals found in equipment like pumps, motors, and fans. Because this equipment often operates on high-voltage AC power, safety and measurement accuracy are top priorities. A current transformer, or CT, is used to step down high current levels to something that can be safely monitored. The CT's output, typically 0 to 5 amps, is then connected to a signal converter that isolates and converts the AC current into a standard 4 to 20 milliamp DC signal. For even greater safety, some setups use a mini CT to further reduce the 0 to 5 amps AC down to just 0 to 5 milliamps, making wiring and handling safer for technicians. Next, we'll look at how digital signal conversion takes these principles even further. Digital signal conversion represents the next step in signal interface technology. Unlike traditional analog isolators and converters, digital converters use data communication protocols to transfer and translate signals, an approach that's especially useful in areas with limited wiring or power. A common example is converting HART digital signals into the Modbus RTU protocol. Because most PLCs and DCSs accept Modbus, this allows HART data, like process variables and diagnostic information, to be easily integrated into control systems that don't natively support HART. Modern HART to Modbus converters not only handle this data translation, but can often power the HART loop using their own 24 volts DC supply. Some HART to Modbus digital signal converters have memory for up to 16 field devices on a single multi-drop network, making digital system integration more powerful, efficient, and connected than ever before. Signal conversion ensures every part of your process, old or new, can communicate reliably by translating legacy signal types into today's standard ranges. Converters don't just convert, they isolate, scale, linearize, and protect signals to keep data clean and accurate. We explored the differences between fixed, field configurable, and PC configurable converters, each offering its own level of simplicity, flexibility, and precision. We also looked at how CTs and mini CTs safely step down high voltage AC signals for monitoring. And finally, we saw how digital conversion maps HART data to Modbus, powers the HART loop, and connects multiple HART field devices on one twisted pair network. Together, these technologies make modern integration safer, smarter, and more efficient.